Problems on relativity. First one, you have to travel to a star 125 light years from the Earth. What would you measure this distance to be? This talks about length contraction and is given by L naught by gamma, where gamma is 1 by square root 1 minus v squared by c squared. So first find gamma. I'm going to correct that to 1 by. There it is. It's 1 by square root 1 minus v squared by c squared. And you get 1.8. Remember that gamma is always going to be greater than or equal to 1. So once you get gamma, plug it back into that and you get 69 light years is what you're going to take. Because you're traveling at that high speed, the length seems to have contracted. In the second question, you decide to travel to a star 65 light years away at a speed that tells you that the distance is only 25 light years. How many years would it take you to make the trip? Again, L is L naught by gamma. Let's find gamma one more time. And from here, gamma is L naught by L. So gamma can be found in two ways. One, from the given information, it's 2.6. And then you take that gamma and plug it back into this relation. Rearrange that and we're going to find the velocity. So you're going to make v the subject. All algebraic operations have to be done carefully, all the more so in relativity. You have to be really careful. Look at the signs and look at how it changes and be very, very careful. So once you get v squared, you take the square root, you get it as 0.923c. So that is the speed at which you are traveling. Now since you have been asked to find how many years it would take, it's a question about the time, and time is nothing but the distance divided by the velocity. The distance that it appeared to be was 25 light years, and because it's light years, that's why it's multiplied with a c there to show it's light years. And then you got the velocity, so the c's cancel out and you get the answer is 27 years. In question 3, the escape velocity is so small compared to the speed of light. Therefore, the expected percent decrease in length of this spacecraft would be really small. And I've tried to do the problem without even taking the original length, because when you're asked to find the percent decrease, you just assume a length, and I've assumed a length of 1 meter in this case, as you can see. So that's again about length contraction. L is L naught by gamma, but this is the value of gamma. So L by L naught is square root 1 minus v squared by c squared. Raised to half. Square root can be written as raised to half, and because this quantity is really small, you can use the approximation where you take the power and multiply it here. So it's 1 minus half v squared by c squared. Remember that only works when that quantity is small. Velocity in meter per second, speed of light When you calculate that, you get this. And as you look at this term, you see that if this were the original length, then this is the decrease. And therefore, in percentage, it's going to be just multiplied by 100. So the percent decrease would be 6.97 times 10 to the negative 8. Question 4. How fast must a pion be moving on the average to travel 25 meters before it decays? And the average lifetime is so small, it's 2.6 times 10 to the negative 8 seconds. And you got to find its velocity. Velocity is d by t or d by delta t now. But delta t is, delta t naught by square root 1 minus v squared by c squared. That goes to the top. You rearrange that equation and you get b times delta t naught by d is equal to this, square root 1 minus v squared by c squared. Square both sides to get rid of the square root. The idea is to separate the velocity so you bring the velocity terms together, take out v squared by c squared, so you have one which is this term written first, and then since you have already taken out c squared and there is no c squared in this term, there is no c squared here, you got to multiply by c squared, and then you have delta t naught by d whole square equal to 1. We're almost there. Now v squared is, you take c squared to the, take all of this to the other side actually, and c squared goes to the top and everything else comes to the denominator. And put it as whole square. So finally, the velocity is square root of this whole thing. Now, plug in the numbers, and we're leaving c as it is because you're going to get the velocity in terms of c, and that is how you have to have the answer. So delta t naught was given, and you have d, so the final answer is 0.95 c. In the fifth question, a particle of mass travels at a speed 0.26 c, and at what speed will its momentum be doubled? So now we know that the final momentum, Pf, divided by the initial momentum is actually 2, but the final momentum is given by mass times Pf by root 1 minus v squared by c squared, because momentum in relativity is actually gamma times mv. So that's why you find that. So, and then do the same with the initial momentum. The masses can be cancelled, and that's given us 2. Square all of it to get rid of the square root. So the right hand side squares and becomes 4. And you take this entire thing over to the right side, and we are given the velocity, initial velocity, or the case where first case velocity is 0.26 c, so plug that in and solve on the right hand side to get 0.29 c squared. Okay, now this is a tricky part because if you were to proceed geometrically, you could isolate Vf from here, but there is a faster method, and that is Vf squared is just whatever you got divided by, add 1 to it, 1.29 c squared with both, and Vf is 0.47 c when you take the square root. Now I'm trying to show how you get that, kind of, because this is like a by 1 minus a by b equal to something called c. And when you solve that, and I'm trying to make a the subject, and you see that you could finally write it as c by 1 plus c by b, which is what we've done. That's number 5. Number 6 says how much work is required to accelerate a proton from rest up to a speed of 0.998 c, and what would be the momentum of this proton. Work required is equal to change in kinetic energy. So work is delta K, and change in kinetic energy is gamma minus 1 mc squared. The reason is because it starts from rest, and we know that this will be the final kinetic energy, and that's the formula for kinetic energy in relativity. That is gamma minus 1 mc squared, where mc squared is actually the rest mass energy of a proton, which you have to know as 938.3 mega electron volts. So that's a number that you need to memorize. And now gamma is this. That is 1 by square root 1 minus v squared by c squared. And you see that the c squareds cancel out from here. That's why you don't have the c squareds. Minus 1, and that number, mega electron volt. You can keep it in those units. When you solve this, you get 13.9 times 10 to the 9 electron volt. Now the second part, momentum. Momentum here is gamma times mv. It is not just mass times velocity. So the factor gamma again comes in there. Another thing is, see, the velocity is written as its energy by c squared, and that's because E is equal to mc squared. You see, E is mc squared, therefore the velocity, it could be written that way. It's a mass times velocity actually. It's written as 938.3 by c squared, gives you the momentum. That's the mass, times 0.998 c. Let me try to explain this again. Mass is energy by c squared. Energy by c squared. And you know that that's the rest mass energy. And therefore, when you divide by c squared, you get the mass. And then you have the velocity. Okay. Finally, on calculation, you get 14.8 times 10 to the 9 electron volt by c. Look at momentum is always expressed as electron volt by c. In the 7th question, you have to find the momentum of a 950 mega electron volt proton. So now you have the energy. You know that the total energy is the kinetic energy plus the rest energy. That is the total energy. Now this is an equation that you get during the derivation that you have to remember. Pc whole squared is equal to E squared minus mc squared whole squared. Okay. Now plug in the value of E into that equation from the above. K plus mc squared whole squared minus mc squared whole squared. Now open that, distribute. You see that the last term gets cancelled. You only have two terms now. First term and the middle term. And then when you take the square root on both sides, you have PC square root k squared plus 2k taken out mc squared. Now why did we do that? Because we know what mc squared is. So when you take out k squared, you get 2mc squared by k. So the problem says k is 950. That's the kinetic energy. 1 plus 2 times mc squared is known to be 938.3 divided by 950 again. So get 1638 mega electron volts. Therefore, the momentum is in the proper units mega electron volt by C. Why? Because on the left hand side you had PC. So when you take C to the other side, it goes to the denominator. Question 8 says, what is the speed of a proton accelerated by a potential difference of 125 megavolt? Surely its kinetic energy is going to be 125 mega electron volts. So this question, once again, you have the kinetic energy. It's 125 mega electron volts. So K is known to be gamma minus 1 mc squared. That's gamma minus 1 mc squared. We know the value of mc squared. And K by mc squared. Because we have to make velocity the subject. You have to separate V now from that. Switch sides and square both sides. I've done both in that step, and finally when you have V squared on one side, it's going to be this equation, and then take the square root. And again, be careful about each step here. C, square root of C squared is C. So now plug in what is given. The kinetic energy is given 125 million or mega. Both will work. Mega electron volts, and you know mc squared is 938.3. So when you do all that calculation, you get 0.470 is the speed of the proton. In question 9, you have to calculate the kinetic energy and momentum of the proton. Mass is given, its velocity is given. If you had been asked to calculate the kinetic energy in classical physics, you would have just gone 1/2 times mass times velocity squared, but we cannot do that. Here kinetic energy is gamma minus 1 mc squared, where gamma is again 1 by square root 1 minus v squared by c squared. So and the speed is given. That's the speed of light, minus 1, and then mc squared is 938.3 mega electron volt. So you have 36.7 mega electron volt as the kinetic energy. And then momentum, remember, is gamma times mv. So just remember what gamma is. Here what I've done is I've tried to take out a c, because you've got to get momentum as mega electron volt by c. So I've already, let me use this. I've already separated the c here, kept it ready, and by doing that I've put another c here, and then that makes me introduce the c squared there. Why? Because I know mc squared. And therefore 938.3 mega electron volt, V by C, both values known. By square root of this, 1 minus the velocity squared. So, which you can write as v by c whole squared, of course. And calculate this, you get 265 mega electron volt by c. Now, if this were done using the classical formulas, this is what you would have got. Just going to run through this because it's just for comparison purposes. All right, so 1/2 mass times velocity squared would have given this 34.6, and you get the momentum as 255. So you calculate the difference divided by the original times 100, and you see that there's a small change. Even at this high velocity, it's not much different. Okay, that brings us to question 10, where rocket A passes Earth at a speed of 0.65 c. At the same time, rocket B passes the Earth, moving 0.85 c relative to Earth in the same direction. How fast is B moving relative to A when it passes A? Now, always set up the equation in such a way that you find ux prime. So there will be 3 objects here, or 3 objects that move. 2 will be the frames of reference, and 1 will be the actual object. Remember how we derived it? So there will be a frame of reference S, and there will be another frame of reference S prime, and S prime will be moving relative to S. And then there is actually an object moving whose velocity measured with respect to frame S is ux, and the same velocity measured with respect to frame S prime is ux prime. I hope you got that. So you measuring the velocity of an object with respect to frame S, call it ux. You're measuring the velocity of that same object with respect to frame S prime, and you call it ux prime. And relativistically, we're trying to go from ux to ux prime. Okay. Now I'm writing down everything. Rocket A is the frame S. The Earth is frame S prime, which means velocity of the Earth relative to the rocket. Why are we saying that? Because we always have to look at the velocity of S prime with respect to S, and we call that V. Okay, so in this case, velocity of the Earth relative to rocket A is actually negative 0.65 c, because from rocket A, the Earth looks like it's going backwards. That's why it's negative 0.65 c. And then velocity of the rocket, B now, relative to the Earth, that's going to be ux prime is 0.85 c. And you have to find ux, B with respect to A, and the formula is ux prime plus V by 1 plus Vux prime by c squared. After you get all that, it's so easy. Just plug in the numbers and calculate carefully. According to the Galilean principles, ux would have been, just the difference, and you would have got it as 0.20 c, which is completely away and off from 0.45 c. I hope you get a good idea of this problem. 11th one. A negative muon is traveling at 43% of the speed of light, collides head-on with a positive one moving at 55%, and the two annihilate and produce. How much energy do they produce? So we're going to use E is equal to mc squared here. Well, the total energy is going to be the sum of the energies of both, because both of them get annihilated completely, and total energy is given by gamma mc squared. Okay, remember that. Total energy is gamma mc squared. Kinetic energy is gamma minus 1 mc squared. Okay, so here's total energy. So take mc squared outside, and we have been given the rest energy, which is 105.7 mega electron volt. So the whole thing is in mega electron volts, remember. So understand that this quantity is in mega electron volt. That's why the final answer is in mega electron volt. How much simpler can it be? Question number 12. Two identical particles are created, traveling opposite directions. Speed of each particle is this. Okay, relative to the lab. Oh. What is one particle speed relative to the other? It's very clear that one is moving along the negative and the other is moving along the positive. We will take the one that's moving in the negative direction as S, and we take the lab, just like we took the Earth and one of the rockets. We're going to take the lab and the one particle that's moving in the negative direction as the frames of reference. So the lab is the S prime frame. So now what's the velocity of the lab with respect to S? It's going to be positive. Why? Because the lab is not actually moving, but this particle is moving in the negative direction. So if you were on this particle that was moving in the negative direction, wouldn't it appear as if the lab was moving in the positive direction? Yes. So that's why it's positive 0.85 C. And now the velocity of the positive particle with respect to the lab, which is our ux prime, is also 0.85 C. So now you can find ux using ux prime plus v divided by 1 plus v ux prime by c squared. Substitute the numbers given and calculate. Get it as 0.987 C. Alright, so those are the 12 questions from Relativity.